Hello, and thank you for your interest in InSync adaptive traffic control from Rhythm Engineering. When talking about InSync, we like to start off with why. Why did Rhythm Engineering invent and now build, sell, and support the InSync adaptive traffic control system? Well, it starts here. It starts with the extremely high cost of traffic congestion. In just the United States alone, $115 billion is wasted in time and fuel by motorists stuck in crowded, busy roadways. That's the equivalent of $731 for every motorist. That is essentially the tax that we all pay for congestion on our roadways. Beyond the monetary cost, there's the environmental and public health cost. Every year, over 80 billion pounds of emissions are exhausted by motor vehicles on roadways. That, of course, hurts our environment, makes our cities ugly, and has a public health cost as well. It makes us sick, and it makes our children sick. But here's the most important number. Each year, there are 30,000 traffic fatalities on U.S. roadways. About 20% of these fatalities occur at intersections. That's 6,000 of our friends, neighbors, co-workers, parents, siblings, spouses, and children that leave in the morning and don't come home at night. This number is far too high, and we can bring this number down with InSync. But beyond these global problems, there are the local problems for the traffic professionals as well. It's those phone calls that you get saying why. It's public officials, local business owners, and there's everyday motorists and citizens saying, why does it seem like I'm staring at a red light when no one's using the green light on the main street? Why, at 6:30 at night every night, does it feel like I'm stuck in the left-hand turn lane for 6 or 7 minutes? Why, in today's age of technology, can I not just drive down the road experiencing green signals? Well, you know why. You have limited resources and limited technology to solve these problems. Why does someone sit on the side street staring at a red signal when no one's using the main? It's because there's a hold on the main street green and you're waiting for the cycle to come back around. Why does somebody feel like they're sitting in the left-hand turn lane for several minutes every night at 6:30? It's because you're going through planned transition. You know these reasons why. You know why traffic management is at its current state based on the resources and technology you have available. But the motorist doesn't care. They just experience the problems. Why can we not drive down the street experiencing green lights at each signal? It's because signal timing is difficult and there are limited resources to do it. And even if you had those resources, the technology available to accurately and precisely time corridors is not available. We know that traffic professionals always have more work to be completed than there is time and resources to complete that work, and that affects signal timing. And that's why we exist. Rhythm Engineering is here to empower communities with innovative and affordable traffic solutions to save time and money, save the environment, and save lives. The InSync adaptive traffic control system does just that. And what we're going to talk about in the next few minutes are these following topics. First, we're going to see field results from agencies nationwide who have deployed InSync, actual real-world examples of InSync's performance and benefits to communities. Next, we're going to take time to understand how InSync works, both the components and the architecture, as well as the concept, the models, and the algorithms. Finally, we're going to take a look at the financial investment and the financial benefits of deploying InSync. First, we'll look at the actual results from field deployments of agencies across the United States. When considering InSync's deployment history, it's important to note that we are the most widely deployed adaptive traffic control system in the U.S. Every day, over 2 million vehicles roll through InSync intersections, and that's because we've been selected for use on over 800 intersections on 140 corridors in 69 cities and 22 states. What this means to you is InSync has a broad breadth of experience already built into the product. We've seen various roadway geometries, agency objectives, motorist expectations, weather environments, integration with existing hardware and software. All of this experience already built into the InSync product to benefit you. We're going to look at several measures of effectiveness from before and after studies performed on InSync deployments. It's important to note what the before conditions were prior to the InSync installation. As you can see here on the screen, by and large, most of these roadways were operating on coordinated time-of-day plans. So when you see the measures of effectiveness, you have to think of it in context as being above and beyond what existing coordinated time-of-day plans were able to accomplish. Some of these plans were very recent, specifically for the purpose of measuring InSync as compared to well-timed corridors. Other time-of-day plans were older, as the agency sought to avoid the expense of updating its plans simply to measure it against InSync. It's also worth pointing out that by and large these studies were performed by independent third-party engineering firms, some of the biggest names in traffic engineering across the country. These are not Rhythm Engineering's numbers and not Rhythm Engineering studies. These numbers were provided by third-party studies or the individual traffic agencies themselves. All of these studies are available on our website for download. The first measure of effectiveness that we'll look at is stop reductions. You see these measures reported in two ways. First, we have an overall number, or average, across all times of day inside the green circle. And then, adjacent to that circle, you see a smaller number. That's InSync's best peak time performance. As you can see with stop reductions, InSync was able to reduce stops anywhere from 21% all the way up to 88% on average, and in individual peak times up into 100% in several instances. The next MOE that we look at is delay reduction, reducing the amount of time vehicles spend waiting at red signals. Again, we can see consistently strong performance from InSync in these before and after studies across the country, reducing delay anywhere from 24% all the way up into the 80% range in some instances on average. Individual peak time results reaching up to almost 90% reduction in delay. The next measure of effectiveness that we look at is travel time reduction. As you can imagine, with stops being reduced and delay being reduced, we see a significant and consistent reduction in travel time in InSync deployments. From 9% as compared to a recently well-timed corridor, all the way up to 50% in one peak time. The next measure we'll look at is fuel reduction. As we stop less and idle less, as we can tell from looking at the reduced delay, vehicles consume less fuel on these corridors. This obviously has a very important environmental impact as well as an economic impact, as motorists are able to keep that money in their pocket and circulating through the community as opposed to in their gas tank and out their exhaust pipe. With less fuel consumption, we see emissions reduced as well. Emissions reductions range from anywhere from 1% in one instance all the way up to 43% in one particular peak time. Again, this has the important environmental benefit as well as the public health benefit. If you quantify the benefits of just time and fuel, we see InSync returning millions of dollars each year back to its communities and its taxpayers. At the end of this presentation, we'll talk more about the benefit to cost ratios and ROIs. But there's another set of data we haven't looked at yet, and that's this: InSync's ability to increase safety by reducing crashes. The NCHRP 403 report draws the correlation between adaptive traffic control systems and safety improvements. We've taken it a step further and collected actual crash data from InSync corridors. What we see from those corridors is a substantial and strong and crucial reduction in accidents along those corridors. Anywhere from 17% in one instance all the way up to 30% in another instance. That's the equivalent of dozens of crashes every single year, avoiding property damage and the time lost to accidents, avoiding the economic impact to the city and public works and emergency services that are associated with accidents, and of course reducing injuries and saving lives. But beyond the numbers, there's the important feedback of the deployment partners themselves. Not only the performance of the system on the roadway, but what was it like in the community? How did it benefit the agency? What was it like working with Rhythm Engineering and deploying InSync? So we've brought together just a sample of that feedback for you here. You can find much more of it by contacting the individual deployment partners. We make all of their contact information available on our website so that you can contact them directly.
The InSync system is performing great. We have gotten results back from 2 of our corridors, and the numbers look great. The travel time and the number of stops has improved dramatically. So it has met our expectations.
Does it work? That's the first question everybody asks. The application we use it in, it works great.
It's performing great. As far as expectations, we have initial before and after studies that show our travel times are in the 30% reduction range. Our speeds are up 30-35%. Stops are down, over 50%.
It's working. It's doing a real good job with it too.
It works exactly like I expected. If you say, does it work better? No, because I expected that I was going to get all green lights, and that's what it's doing.
The improvements that we saw were far and beyond what we expected. We reduced the travel times through the corridor by anywhere from 40% to 70%.
Traffic's moving in all directions. It's optimizing as it's supposed to.
And after putting in 2 corridors here now and having the experience of it, and looking at installing another 3 corridors, I see the benefit of it. It's easy to install. Use the existing equipment that you have there and add the InSync processor.
The input from our staff and from our time into the system is very little, very minimal.
Yeah, we feel that the ease of installation, the ease of maintenance, and the benefits you get from the improved traffic flow is just remarkable in my eyes.
From the minute we met them, Rhythm was very helpful. Anytime we have any questions about anything, we give them a phone call and they get right back to us and answer any questions.
Our InSync was in place approximately 3 weeks before Black Friday, and it handled traffic just perfectly without having to do any kind of manual overrides or adjustments to the system at all.
A lot of positive feedback from our residents. They, especially people who are on the side streets, have noticed that they do not wait as much. They're able to get through the intersections much easier. We have also seen a dramatic improvement in the travel time on the corridor itself.
Basically what we're saying is we're getting pretty much the side streets clearing real well. We're also handling Main Street traffic well.
We got rave reviews from not only the public officials, but as well as from the motorists.
The response from the public and city leaders has been very well received, real supportive. If you drive the corridor, you see a change.
No calls are good. That means it's doing what it's supposed to be doing.
I know the system is doing its job, and I know people are a lot happier with it than they were with anything we've tried there before.
There's a whole lot less congestion today than what we typically see. And that's the goal for the whole corridor, is to reduce congestion, much more so than we can do with traditional traffic timing plans.
Traffic engineers know how difficult it is just to squeak another 5 or 10% out of a signal, out of its capacity of a signal, just doing very minor things that they can do with timing and those sorts of things. So when you see these types of gains, the numbers will speak for themselves.
In one time frame, it's dropped almost, it's in the 90%, the amount of stops that have dropped. And that's just phenomenal. Usually you're looking at 15%, 20% is great numbers, but having them up to the 90s, that's just, I'm impressed.
I know the travel times were up to 8 minutes before, and I think we've got them down to 3 or 4 minutes.
Just like it advertised, drive the entire corridor on green lights.
InSync works and has made a huge difference.
It's working well for us.
It worked well, just day one.
If you're considering an adaptive control system, that the Rhythm system is the best on the market.
I would definitely recommend InSync to other cities.
InSync works. It made a huge improvement.
Now that we've heard some of the experiences of individual InSync deployment partners, we at Rhythm Engineering have something to say about the experience and the performance of InSync. We call it the InSync Promise. The InSync Promise is our money-back guarantee to you that if after 3 months of adaptive operation you do not feel our partnership has had a positive impact in terms of reduced travel times, emissions, fuel consumption, and improved safety, we will issue you a full refund. That is our commitment to the success of our deployment partners and, of course, the InSync product. Now that we've looked at field results from across the country and the experiences of those individual deployment partners, next we'll take some time to understand how InSync works and achieves those results. First, we'll look at it from the architecture, the pieces and parts, the components of the system, and how they come together and interact with each other. When talking about the components of InSync and its architecture, we like to start by pointing out that InSync was entirely invented and is designed, assembled, configured, and supported directly by Rhythm Engineering. The people who built the product and configure it every day are the same people that you will contact should you ever need support. And what we find is deployment partners often choose InSync the first time because of its high performance and the measures of effectiveness and feedback that you just heard, but come back to us over and over again because of the strong support and assistance and sense of partnership that they receive from Rhythm Engineering. We also like to point out that Rhythm Engineering is a 100% American company. So as we get into the components and how they come together, here is the basic look at the architecture of the InSync system. It starts with detection inputs. Now here on the screen I'm showing a camera, but as you'll hear more in a minute, InSync is 100% compatible with all forms of vehicle detection. When those detectors detect the presence of vehicles as well as the number of vehicles and how long they've been waiting or the delay, it sends that information into the InSync processor. The InSync processor resides at each individual traffic cabinet. It is performing the algorithms and the decisions and feeding the information into the controller. It does that by picking the most appropriate state or phase pair based on actual traffic conditions in the moment. Not what happened in the past, not what happened in the last cycle, but based upon traffic conditions at that moment, how should the signal be serving traffic? It then delivers that state or phase to your existing controller in your cabinet that is running entirely in free mode. This has several benefits to you. First of all, you get to continue using your existing controllers and cabinets because InSync is 100% compatible with all modern controllers and cabinets. 170s, 2070s, NEMAs, TS1s, TS2s, NEMA style cabinets, 330, 332, 336 style cabinets. We are 100% compatible with all modern hardware that currently is running in the field. Because InSync is an overlay system leveraging your existing technology and hardware, it also installs very rapidly. The plug-and-play architecture can be installed within just a few hours per intersection. In the event that you choose our video detection along with your InSync system, it can typically be installed about 4 hours per intersection. If you go with our InSync Tesla option, which uses your existing detection, we've seen it installed in as little as 15 minutes per intersection. All of your existing hardware that your signal techs and that you are familiar with remains in the cabinet. Things like your emergency vehicle preemption, your conflict monitor, etc. remain in your traffic cabinet. You'll also note when looking at this simple architecture on your screen that nowhere do you see a central server or central command. That's because InSync leverages a truly distributed network of intelligence. That provides InSync more rapid response to traffic conditions as well as a more robust architecture in that it is not dependent upon the operation of a central server or communications with that central server. There are several different configurations for InSync's detection. The first is the standard InSync system. It comes with our provided video detection cameras, up to 4 per intersection. These cameras not only detect presence, but also measure queue length as well as delay. They have the added benefit of providing you live, real-time monitoring that we'll talk more about in a minute. The second detection configuration of InSync is InSync Tesla. InSync Tesla leverages your preferred detection devices, whether they be inductive loops, third-party cameras, video systems, radar, magnetometers, or microwave. As long as we have stop bar detection for each approach at each intersection, we're able to use any type of existing or preferred detection. The third detection configuration is InSync Fusion. InSync Fusion leverages the best of both of these previous two. It provides the agency with the cameras as well as leverages your existing and preferred detection, usually in the form of physics-based detection like inductive loops. This has a couple benefits. First, you get the benefit of the live monitoring available through InSync's IP cameras, and you get the accuracy of your existing physics-based detection. Another benefit is you have built-in detection redundancy should either set of detectors have trouble. The other input that InSync takes in as far as demand is pedestrian demand. The InSync pedestrian module receives and holds pedestrian calls at each individual intersection and then schedules and serves pedestrian movements along with the best concurrent vehicular movement so as to not disrupt traffic flow on the corridor. InSync's distributed network requires communications both between each intersection cabinet as well as remote communications into the corridor. About half of our deployments are running on just a twisted pair of copper, so Ethernet over copper, and other deployments, of course, are running fiber as well as wireless. This results in a very robust architecture. First, because of the distributed network and the intelligence built into the InSync systems, a loss of communications results in no change to the performance and operations on the traffic network. Should the processor itself go down for any reason, it's able to submit detector calls directly to the controller, which remains in the cabinet, which can run coordinated time-of-day plans or simply fully actuated. One of the unique benefits of InSync is our patented mitigation for loss of detection. InSync includes intelligence to rely on historical data inside a 5-minute period by time of day and day of week to continue to serve traffic efficiently should any detector fail for any reason. It does not need to roll back into a fixed timing plan or simply running free and fully actuated. Now that we've looked at the InSync components and architecture, let's take some time to understand the model and software running on that architecture. We didn't invent adaptive traffic control. In fact, it's been around for decades. The first adaptive system was in the 1920s in Detroit. It was a human being in a signal tower. That human being had the benefit of being able to see demand, assess delay, anticipate arrivals, and control the signals dynamically in the manner that best fit demand at that individual intersection. This created a very flexible, fluid, dynamic, and immediate signalization routine. Of course, as automobiles became more prevalent and intersections more widespread, agencies found that it was cost prohibitive to put a human being, a traffic cop, at each individual intersection and turned instead to mechanical devices and eventually to electronic devices to control signals. And what you're going to see here in the next couple of minutes is we've returned to that flexible, fluid, dynamic method of controlling signals. We first do it by abandoning the analog or mechanical concepts and thinking and turned to digital thinking and digital concepts. The next thing we did was built what we call a local optimizer. It optimizes traffic at each individual intersection. And then we have a global optimizer that optimizes traffic flow to meet agency objectives along the entire network. So what do we mean when we say going from analog to digital concepts? Some of you may be familiar with this device. This is an electromechanical controller, and these were used after those traffic cops and for several decades following. It was a mechanical device that had a dial in the center, that round circle that you see there. That dial turns around and completes a revolution every so often. That forms the cycle length. Those pins or keys that you see stuck into the dial actuate the signals. What you end up with is a very fixed linear sequential method of signalization. Today's modern digital traffic controllers, they're solid state, they have digital interfaces and screens, but at their core, they continue to think like this. They think in terms of fixed cycle, fixed sequences, linear, sequential method of signal operation, when in fact our technology has gone beyond that and it's no longer necessary to think in that way. We like to make the comparison to televisions. 20 or 30 years ago, in order to change the station on your television, you had to get up off the couch and walk across the room and grab hold of the big knob. And in order to go from channel 7 to channel 11, you had to click through channel 8, channel 9, channel 10, landing on channel 11. A very sequential, fixed operation to get to where you were going. Today's modern televisions, of course, you grab the remote, you punch in channel 1023, and your television automatically goes there. That's because modern televisions are state machines. State machines have been around for decades as well. They simply are an electronic device that takes in some input, has a decisioning mechanism built into it that creates some output. In the case of the InSync state machine, the input that it takes in is traffic demand. And we do it by looking at the quantity of vehicles demanding service at any approach and the delay of those vehicles at each approach. InSync then uses its decisioning algorithm to determine which output to create. Of course, the outputs in traffic are phases and oftentimes phase pairs. InSync is able to dynamically decide between the various phases and therefore sequences how best to serve traffic at that moment. Here we'll give you a quick example, and I hope what this illustrates is not only how dynamic InSync is, but also the real-time nature of InSync. You'll notice that I keep saying that InSync is making the decision immediately, not based upon what happened in the last cycle or what happened over the last several minutes. Let's imagine this Monday that traffic demand indicated that the greatest need for service was at the northbound left and the northbound through movements. Next Monday, at the exact same time of day, the greatest demand was for the southbound through movement and the northbound through movement. This is the first adaptable mechanism of InSync. It's able to adapt the phasing based on actual demand. Once it's decided which phase or state to bring up, it then chooses an appropriate sequence. In this example, we'll assume that all the lefts are protected left turns, just to make the example easier. So here we see the second way InSync is adaptive. Based upon the phasing, it then schedules an appropriate sequence. However, what you'll see here in a second is that it's not married to that sequence, and it has the ability to change what it's doing inside that sequence as well. Once the phase is determined, it then looks at the number of vehicles and its knowledge of that individual intersection as far as safe clearance times, and determines how much green time is needed to be served to that phase pair. We'll say in this first example it needs 25 seconds in order to serve the northbound left and the northbound through. Of course, knowing that its next phase may also serve that northbound through. What the InSync processor finds is that it was able to effectively clear the northbound through queue such that, given the knowledge that the final phase in the sequence includes the southbound through, it can omit that through phase and immediately proceed to the next phase, the southbound through and the southbound left, giving it 32 seconds of green time. So here we see the third way in which InSync adapts is by its distribution of green time based upon actual demand at that moment. Now next week, traffic conditions may be slightly different, as is common on any traffic network. The first phase is served 43 seconds. Knowing that the northbound through phase is going to be served again, the system brings up the next phase pair for 17 seconds, and recognizing that it has effectively cleared the northbound left and that there is no demand for the southbound left, it's able to omit that phase Because InSync is not operating on a fixed cycle or sequence, it is of course able to go back and reserve a phase as needed. So as demand becomes recognized at a certain approach, it can schedule an appropriate phase or phase pair to serve that demand when it arrives. That is how the local optimizer delivers the first three adaptive attributes of InSync: the dynamic phasing, dynamic sequencing, and dynamic green time, including omission. InSync's global optimizer solves for the agency's objectives along the entire network. Oftentimes, these objectives are things like queue management, progression, and throughput. Here we're going to understand the concept driving the global optimizer, and we do it by looking at this time-space diagram. We have time mapped across the vertical axis and distance or space mapped across the horizontal axis. The dotted lines up and down the screen represent individual intersections. The two arrows in the screen are the speed lines. They show traffic moving in opposite directions along the same roadway. Because they are moving across both time and space, they become speed lines. As platoons of vehicles naturally gather at the beginning of the network or corridor, InSync recognizes them and releases them through the network, telling each downstream signal to prepare for the arrival of the group of vehicles. In this way, InSync can optimize traffic progression, service, and green time allocation by having groups of vehicles arrive to a green signal, as opposed to having them stop and then waste time on startup for them to clear the intersection. Vehicles can move efficiently, nearing free flow speeds through the entire corridor without stopping. Because vehicles are moving efficiently through each signal using the green time to its maximum potential, there is then more green time to use, either progressing more vehicles through the corridor or serving the minor movements. InSync schedules these green tunnels across the time periods of the day based upon demand. This is the next two ways in which InSync is adaptive. The frequency of these green tunnels or serving the coordinated movements is dependent upon volume and demand. They are also adaptive at each individual intersection in the duration that the coordinated movement is served. It can expand or contract the amount of green time served to the coordinated movement. These are the final two ways that InSync is adaptive: the frequency of the coordinated movement or green tunnel, as well as the duration of the coordinated movement or green tunnel. Now, the relationship between the local optimizer and the global optimizer is this. We call the amount of time between serving the subsequent coordinated movements a period. Inside this period, first, the global optimizer solves for the global objectives serving the coordinated movement. It then turns control over to the local optimizer. The local optimizer, as we've discussed, looks around the intersection and says, where is the greatest demand right now? For instance, let's say it's now on the side street through movements. It will serve them the appropriate amount of green time to clear their queues. It then looks around and says, now where's the greatest demand at the intersection? It's now on the main street left turns. So it serves the main line left turns, the appropriate amount of green time. It then looks around and says, do I have time to serve another local movement before the coordinated movement? Yes, indeed I do. Where is the greatest demand? Well, it might be on the main line movements. It might be the side street left turns. It might be back on the side street through movements. It's able to dynamically choose which movements to give service to based upon actual demand as measured by quantity of vehicles and delay of those vehicles. It serves the appropriate movement. It then says, do I have more time? I do not. The coordinated movement is about to come through. It turns control over to the global optimizer. It serves the coordinated movement for the appropriate amount of time, and then the process repeats itself. So in this way, InSync continues to adapt to actual real-time traffic conditions throughout the day. What we end up with is a model that we describe like this. InSync runs intelligently fully actuated intersections to optimize all approaches. And what we mean by that, unlike a traditional fully actuated intersection that's running free, we understand not only presence, but also the quantity of vehicles that are there and how long those vehicles have been waiting. And at the same time are able to serve coordinated progression along the entire corridor. So in this way, it's a best of both worlds strategy, minimizing movement delay and control delay at each individual intersection, while also creating the benefits of dynamically coordinated progression or throughput along the entire corridor. One of the benefits of the dynamic nature of InSync is the substantial minimization of transition. Because InSync is not running a cycle, and because InSync is not running time-of-day plans, and is immediately adapting to real-time demand inputs, it does not suffer the transition like other systems do. It is immediately able to recognize the current traffic conditions and manipulate the signals to accommodate that traffic demand. So either in the events of preemption from, like, say for instance, railroad or emergency vehicles, or what other systems would do as far as transitioning from time-of-day plans, InSync experiences none of those negative effects because it does not go through that type of transition. InSync also has numerous applications. It's not solely a progression along an arterial solution. Different applications as far as geometries go include arterials, crossing arterials, traffic networks, freeway entrances and exits, odd signal spacing, and unique geometries. As far as conditions InSync can solve for, things like high variability, saturation or capacity limits, and special events. InSync is also able to solve for a number of different objectives, things like safety, environmental impact, throughput of the network, bidirectional progression, traffic calming, queue reduction and management, high non-vehicular demands such as pedestrians and bicyclists, simply automating timing so that the signals don't have to be retimed every so often, which is particularly applicable in high development areas. And what's interesting about the list that you see here on the screen is this is not theoretically what InSync could do. InSync is actually solving for all of these applications in the real world today. Now we keep talking about how smart InSync is. Well, it only knows so much, and it doesn't know what you know about your local corridors, their geometries, your motorist expectations, and especially your objectives. And that's why it comes with the companion software, CentralSync. The companion software to InSync, which includes both CentralSync and the web UI, allow you to see InSync's current configurations and parameters as well as what objectives it's seeking, give input to those things, and hear from the system as far as performance levels, data being put into the system, and alerts and alarms of special activities and events. Here we see the opening screen typically of a CentralSync session. You see the InSync equipped corridor, each intersection represented by a node on the map where you can zoom in and see the specific parameters and configurations for each intersection, as well as see the global configurations and parameters in a couple different ways. Here we see the time-space diagram. Through CentralSync, you can give the system inputs as far as what concurrent phase pairs you would like to permit at each intersection by time of day and day of week, as well as which sequences you would like to allow or disallow, again, by time of day and day of week. A lot of agencies are particularly interested in this screen as far as whether they should lead their lefts, lag their lefts, or allow a lead lag if the optimizer determines that's the best sequence to institute. Sometimes people ask, if there's constant demand on the main line, does the side street or the left turns, the minor movements, do they ever get served? And of course the answer is yes. There are a few different ways to do it, and one is through what you see here by establishing a maximum wait time for any given approach that essentially overrides the optimizer's decisioning and serves an approach potentially more rapidly. CentralSync will also take in the inputs of so that it has knowledge of what the minimum settings are in your controller. It certainly cannot override the minimums, although it can extend them. as far as the green times, amber, red, and therefore the change times for each movement. Now through the Web UI interface, which is available through any common web browser, you're able to do a number of things. The first is pull up live camera views of each of your InSync intersections and approaches, like you see here. You can also access each individual InSync processor in the cabinet, which allows you to do some diagnostic activities, as well as see the detection inputs going into the InSync processor, and should the situation ever warrant it, you can always place manual calls as well. Because the InSync system is running on data, we can of course make that data available to you. That is done through the screen you see here. You pick a date range and a time range and then ask or indicate what type of data you'd like to see, counts, delays, level of service. You can then see that information either in a graphical display inside the web UI, or see it through downloads such as a CSV or Excel file. Finally, the last piece of information that you can get through the web UI is what we call the history viewer, and it allows you to see what the InSync processor was doing on a specific day inside a specific time range. So if you get a call that says, you know, this morning on my way into work at, I don't know, about 6:45 a.m., the signal was doing something in particular, you can pull up this view and see exactly what was going on at that intersection, as far as the demand on the other phases, what phases were actually being served, whether there was a pedestrian call or any type of preemption at the same time. You can see all that information through that tool. And finally, Central Sync will reach out to you and tell you if anything out of the ordinary is going on. You can set up alerts and alarms configurable by time of day, day of week, type of event, and the recipient, as well as what type of message, whether it's a text message or an email, that InSync will send you if it sees those events going on. So it will proactively reach out to you and tell you when it sees one of these events occurring. So we've looked at the results of InSync deployments from across the United States. We've taken some time to understand how the system works, both its architecture, components, model, algorithm, and companion software. The final section we'll look at is the financial investment required to get InSync up and running on your networks, as well as we'll look at the benefit cost ratios. Rhythm Engineering believes in very transparent and clear pricing of our products, and that stems from the fact that our founder, and then therefore our heritage, resides in the public sector. We know surprises, especially financial surprises, along a project are very detrimental to the progress of benefiting your community, so we try to get all of the information to you up front. First of all, you see the pricing of the various systems on a per intersection basis. InSync, that comes with our up to 4 cameras per approach, is $25,000 per intersection. InSync Tesla, that uses your preferred detectors and can leverage your existing detection systems, is $25,000 per intersection. InSync Fusion, that leverages and delivers both our cameras as well as your existing detection, is $30,000 per intersection. There's the pedestrian module if you have pedestrian demand at a given intersection for an additional $5,000. And each deployment comes with a project management fee that is typically $1,000 or less per intersection. Now there are other things that you should consider as well. The other big costs for deploying any system is the communications and the installation itself. And there are other ancillary peripheral items that you should take into account, such as the mounting hardware for the cameras, various cabling, shipping taxes, spare systems, etc. We are more than happy to provide you a firm written quote for your specific deployment so you know exactly what the cost will be from Rhythm Engineering. Now that we've taken a look at the financial investment for an InSync deployment, we can begin to think of it in terms of benefit to cost ratio. Now we have a lot more information available on this aspect other than what you're going to see here, but we want to give you a taste for it. Here we're looking at one of our deployments that has the benefit of enough time and enough data gathered that we can look at a fairly comprehensive benefit to cost ratio. Looking at the InSync cost as being fixed over the first 5 years, knowing the safety benefits and their associated economic benefit for both the community as well as the agency, and of course the traffic benefits of reductions in stops, fuel, and time, we're able to derive a total financial benefit. We see in the first year alone of the deployment of this system a almost 23-to-1 benefit to cost ratio, and as those benefits continue to accumulate year over year, in the first 5 years of deployment of this system, it's going to return to the taxpayers and the community at about 114-to-1 benefit to cost ratio, and of course continue to deliver benefit after the 5th year. We look at another deployment, our Missouri 291 in Lee Summit, just outside the Kansas City area. The initial cost of the InSync system there was $200,000. The crash reductions led to a benefit of $1.2 million a year. The traffic benefits, again the stops, time, and fuel, almost $2.5 million per year for a total benefit of $3.7 million per year back to the community. In the first year alone, that's greater than 18-to-1 benefit to cost ratio, and across 5 years we see greater than 92-to-1 benefit to cost ratio. So this is the types of benefits and the investment quality of an InSync system delivering benefits back to taxpayers and the community at large. All right, now that we've taken a look at field results from across the country, understand how the InSync system works, and looked at the financial investment as well as the benefit to cost ratio, I hope what you take away from this presentation is that InSync is chosen by more agencies than any other adaptive system. It has been fully validated. It's a mature product based upon experiences and feedback from clients as well as independent third-party engineering studies. And those studies show that InSync is able to deliver dramatic improvements in traffic conditions. Looking at how InSync is able to do this, it's because it utilizes real-time local and global adaptive traffic control. We put the emphasis on real-time as InSync is able to make changes in the moment, second by second, not the next cycle, not several cycles later, but can respond to actual traffic conditions that moment as they are present at the intersections and throughout the network. It's compatible with all existing hardware, and it is, of course, powerful, patented technology. On the economic side, we believe it's very competitive pricing, approximately the same price as a detection system, but of course it comes with the unmatched adaptive abilities of InSync. There is no active operation of the system. You heard some of the deployment partners speak to that earlier. They don't have to manage this system and sit down and run it every day. It pretty much takes care of itself. There are no timing plans to build and maintain. Unlike other adaptive systems that require good timing plans and the maintenance of those timing plans, you're not going to have to go out and create new timing plans and maintain those timing plans for InSync to deliver these kinds of benefits. And this is substantial ROI, or benefit to cost. We looked at that here at the end. Obviously a very powerful investment with taxpayer dollars. Ultimately, what you're going to find with InSync is you're going to save motorists time and your agency's time. You're going to save motorists fuel. You're going to save your agency's money as well as motorists' money. You're going to save the environment. And most importantly, we're going to save lives. Again, we appreciate your interest in the InSync Adaptive Traffic Control Solution. You see here on your screen contact information for us. We hope that we can perform a corridor analysis for you and look at your specific target deployment. Not only let you know the costs and pricing for that, but also how InSync will perform and how good of a match it is for that particular deployment. I do also want to point out some of the additional materials that we have available on our website that greatly expand upon some of the points we've talked about in this presentation. First off, there's the InSync white paper, which is a full discussion of all of the various components, pieces, parts, algorithms, and case studies of InSync deployments. We have all the full before and after studies available for download from our website. You can see videos of actual deployments and Reggie Chandra, our founder and CEO, talking about the InSync model, software demos of Central Sync and the Web UI. We have the Adaptive Traffic Control System Grant Funding Playbook, which will help you find funds for your InSync deployment, and the 2012 Corridor Management Report, and much more. Thank you again, and we look forward to working with you in the future.